So in today's webinar, we'll cover a number of topics. First, we're going to cover the concept of viscosity fingerprinting. After that, we will discuss briefly the way that we have to measure viscosity, which is actually using VROC technology. So we'll cover it briefly. And then we will focus on Initium. We will explain some of the instrument capabilities and some of the specifications. We will go through some of the measurements that we have done so far using the instrument, mostly in protein formulations. I will give some additional details that were not present in our previous webinar that I forgot to mention you can access through our website as well, on the software and the applications for the instrument. So most of you are probably familiar with the concept of viscosity, which is the resistance of a fluid to flow and how it can be related to molecular properties of different formulations. Maybe some of you are familiar with the concept of viscosity fingerprinting, which is very similar to the idea of viscosity screening. So essentially, you might want to use viscosity as a good parameter, a good indicator of a number of properties in your formulation. And there might be a number of parameters that you might want to change, and you might want to study the effect that they have on the viscosity and on the properties of your formulation. So in order to tackle such a task, we require an accurate and reliable method to measure viscosity. We require it to be fast, but for large number of samples where you're going to be studying 2, 3, 4, a number of parameters that you're going to vary over a spectrum, you're going to need to add automation to that accurate, reliable, and fast measurement of viscosity to be able to test this large number of samples in an unattended way. And that's the idea behind VROC Initium. So further developing in the idea of viscosity fingerprinting, you might have a formulation or a protein or a monoclonal antibody that you want to study, and you might want to look at parameters such as what's the effect that the viscosity that you can see in the viscosity based on the concentration of my formulation. So that's one parameter that you can look at. You can look what's the effect of the pH of my buffer solution. What's the effect of the different buffer solutions that I can use? What's going on in my formulation if I'm adding different excipients? Some of you might add sucrose to your formulation. Some of you might add L-arginine. Some of you might add something else. You can also look at the effect of parameters such as temperature or shear rate. They can play a role on the actual viscosity of formulations. You might look at the effect of the naturans and see how your proteins are unfolding and how that's affecting the viscosity of the formulation. And in summary, you can look at any other parameter that you can think it's affecting your formulation and that you might be interested on. And for to be able to do such a study, you're going to need a way of performing this large number of measurements in an automated way. And that's what VROC Initium has to offer over non-automated viscometry methods. So the main applications that we target with this instrument are viscosity screening, injectability of either Newtonian or non-Newtonian therapeutics, characterization of the molecular size of formulations through measurements of intrinsic viscosity, and characterization of the stability of different formulations. Now, how do we measure viscosity? All our instruments are powered by VROC technology, which stands for Viscometer, RheoSense on a chip. The principle of operation is very simple. You have this combination of a microfluidic channel with a MEMS pressure sensor array. So you're going to control your flow rate as you pump the fluid through the rectangular slit microchannel. And since you know the dimensions of the microchannel, your shear rate is going to be proportional to the flow rate that you're controlling. On the other side, at the bottom of the microchannel, you have this array of pressure sensors that are going to be able to measure the pressure as a function of position in your microchannel. That pressure drop that you're measuring is going to be proportional to the shear stress, and by definition, viscosity is the ratio of shear stress to shear rate. There is a number of features or advantages that come just by the design of the device or the technology. One of them is that you are able to measure absolute viscosity, and you're able to measure it at a controlled shear rate. So it allows you to characterize non-Newtonian samples, which is something that most viscometers lack. The next two ones are related to the size of the device or the microchips. So these microfluidic channels are very small in size, and that's going to allow you to, one, do measurements with very small sample volumes. In the case of VROC emission, you will be able to get as low as 10 microliters of sample loaded into the instrument. And it will also allow you to do measurements at very high shear rates. That's because the small size of the device is going to result on a very small Reynolds number that is going to be very low up to very high shear rates. In addition, this is a flow-through design, so your sample is going to be flowing through the chip, so you can do multiple measurements with the same loading of the sample, and that's going to render a very high throughput. And the technology is very precise and offers superior repeatability and accuracy. Our accuracy spec is 2% of reading. Our repeatability spec is 0.5% of reading. And that's independent of the instrument that you're looking at, because all of them are powered by VROC technology. In terms of the dynamic range of operation, this is a graphic representation. We offer a number of different chips where we change either the channel depth or the membrane of the chip, and that allows you to measure roughly between 0.5 inverse seconds and 1.5 million inverse seconds, depending on both the viscosity of your sample, the chip that you're using, and the shear rate of interest. The white dashed line that you can see here as a limitation in the viscosity is motivated by the autosampler. So we know that you can automatically test or test in an automatic way samples up to 1,000 centipoise. If you were to require to test some very high viscosity sample, that will be doable with the instrument. You will just need to manually load that specific sample. This is a similar representation where we actually show what's the shear rate of interest depending on different applications. You can see here how we have injectability at pretty high shear rate, stability, and medium range of shear rates, and some other industrial applications as in injetting or lubrication and so on, at different ranges of shear rates. And you can compare those to the normal or standard range of operation for rheometers and for VROC technology, or VROC emission in this case. So now focusing on the instrument, VROC emission, here are some of the key features. You can see the instrument in this very nice render. We have a high throughput automatic Viscometer rheometer. Everything is fully automated. I will explain that in a later slide. You can measure samples with as little as 10 microliters, which is the smallest sample volume requirement for a measurement of viscosity in the market. The instrument is compatible with 40 vial rack and 96 volt plate. You can do shear rate and temperature sweeps. The instrument has two built-in Peltier temperature control for the test syringe and the VROC cell that allow for temperature control between 4 and 70 degrees. And we have the third Peltier control for the sample rack that allows you to keep your samples while the other samples are being tested between 4 and 40 degrees Celsius. Here you can see different components of the instrument. You have the XYZ autosampler that is going to be in charge of loading your samples, retrieving your samples, and so on. You have the main VROC Initium unit, which is where the measurements of viscosity are going to be performed. You have a status indicator, an LED. You have 3 different solvents. You have a primary solvent that is going to be compatible with your sample, an optional secondary solvent that we might use to increase the speed of cleaning, and a dryer enhancer that we use to speed up the drying of the different pads in the instrument. All those have a weight sensor under it, so the instrument will display a warning when you're running out of solvents for your cleaning. And now let's go into the details of how the measurement and the automation process is taking place. You're going to have your 40-valve rack or your 96-volt plate into the rack place. Those are the 2 standard racks that we're working with. There's no reason why it cannot be customized to a different kind of rack or plate, such as 384 or similar. So you're going to have your sample set up there. You can set up the temperature between 4 and 40 degrees. The XYZ autosampler is going to come to whatever sample you have determined, load it into the autosampler syringe, and then it's going to move it into the 100 microliter syringe injection port. Once your sample has been loaded, the instrument is going to take it to the temperature that you want to test at, wait for temperature stability depending on the selected criteria that you have set up during your measurement protocol, and then test your sample. You can test the number of shear rates, you can test the number of temperatures, and so on. And then when you're done with your testing, you will have the option of either disposing your sample and direct it to waste, or you will have the option of actually retrieving from a reservoir your sample and loading it back into your vial. Once that either of those 2 steps have been accomplished, you can start with the cleaning. So you will pump your primary solvent through the different pads that you have used during your measurement. Then your optional secondary solvent might be involved in the cleaning protocol, and then finally you will pump your drying enhancer solvent that you will use before pumping air through the different pads to dry the system and get it ready for the next sample. Here's a summary of the dynamic range. As I mentioned, you are able to measure between 0.2 and 100,000 centipoise, but if you're using autosampler and you want to do automatic measurements of viscosity, you are limited by the autosampler loading process, so you can go up to 1,000 centipoise, which is more than sufficient for most applications. You can cover a shear rate range between 1 and 1.5 million inverse seconds, which is really wide compared to other rheometry or viscometry technologies. If you think in terms of a rheometer, most standard units can go up to 1,000, some of them 10,000 inverse seconds, but that's it. So if you want to study things like injectability, then you're very limited. So you can do different type of studies based on this dynamic range. You can test the your sample's viscosity at a fixed shear rate, just to do some viscosity screening of your different formulations. You can do the viscosity fingerprint in terms of the viscosity curve as a function of shear rate for a specific sample, or as a function of temperature, and so on. You can estimate injectability by measuring your sample at high shear. You can use actually the instrument features automatic mode, so you can actually set up your measurements in a way that you just load your samples and the instrument will determine what's the appropriate shear rate, so you don't even need to set up the shear rate for each specific sample. You can just get a good estimate, or you can get a good measurement of viscosity at some shear rate depending on the viscosity of the sample and the chip that you're using. All right, so now we are getting into the measurements part with the unit. We have some results proving the concept of repeatability and accuracy. As some of you probably know, VROC technology is simply precise. So here we have some measurements that we perform with, in this case, you have N2, which is a standard oil, or N10, which is another standard oil, and we have measurements of different shear rates, and you can see how the difference with the reference viscosity, it's well below the spec. You can also see in a repeated measurement, I believe this is for water or aqueous solution, you can see how you consistently can get the same value of viscosity in separate measurements at the same or different shear rates. Next is the proof of concept of the 10 microliter measurement. You can see here in our standard release, which is the release that we're working on right now, the swept volume in the pad between the syringe and the outlet of the cell is about just below 6 microliters. So with 10 microliters, you have sufficient volume to actually prime all that pad and then get a measurement with the remaining 4 microliters of sample. We have an extremely low volume release plan where some of the tubing is optimized to reduce that volume a few extra microliters and even reduce further the requirement of 10 microliters of sample being loaded into the VROC Initium unit. Here you can see how with 10 microliters you can you have sufficient volume to prime your chip, and then with the remainder get a good measurement of the viscosity, in this case of IPA at room temperature. Here we have a first excerpt of measurements of protein solutions. In the left you can see measurements of BSA in PBS buffer solution at different, you have function of shear rate for different concentrations. All these solutions are pretty low in the concentration, so you can see how all of them behave like as a Newtonian fluid. On the right you can see the same data for PBS, BSA and PBS, but you can also see measurements performed BSA dissolved in water, DI water. You can see how there is a small effect by changing the buffer solution that you have. You can also see solutions made with immunoglobulin in PBS. You can see how there's a much more significant effect on the viscosity as you change your protein, as you will expect. So the instrument allows you to do this kind of characterization where you're going to have a large number of concentrations and a large number of different proteins or different buffers and different formulations where you're changing some component of the formulation, and you want to test all those for viscosity. And that's something that you won't be able to do, at least not in a reasonable time way, without automation. Next is an example of measurements of Shantan gum. This is our non-Newtonian sort of standard that we use just because it's a very good example. It's used by the food industry quite a bit, and it's strongly non-Newtonian. So you can see how viscosity is dependent on shear rate, and in this case it's a shear thinning fluid, so you have viscosity decreasing as a function of shear rate. It follows very well a power law fluid, at least in the range that we have studied here, and you can see how well the instrument is able to capture that behavior. I also would like to mention that for this test we did up to more than 20 measurements at different shear rates with a single 100 microliter syringe. So that gives you an idea of the large amount of data that you are able to capture with a single syringe. This is a little more extensive study that we just performed in BSA in water and BSA in PBS. We wanted to look at the effect of both shear rate and temperature. All of these solutions were actually Newtonian, so the shear rate data is not here. We're just presenting an average of the viscosity values over the shear rate as a function of concentration, and later on I will show as a function of temperature. So you have all these different formulations that we prepared with two different buffers, and you can test, as I mentioned, we tested between 20 and 37 degrees, but you can test anywhere between 4 and 70 degrees Celsius, which is a pretty wide range for these kind of applications. This is a closer look at the specific data set with PBS. So you can look at the 3 different temperatures and the different effect on the viscosity versus concentration profiles. As you will expect, at least in this range of temperature, the highest viscosity is for the lower temperature, and as you increase temperature, your viscosity keeps decreasing. If you were to increase the temperature further, you will expect actually your protein to start denaturating and unfolding, and then you will get an increase on viscosity because of that process. Here is the similar set of results for BSA in water. We have one extra concentration here. You can see how after some concentration level, your viscosity actually increase almost exponentially. So if you're working in this range of concentrations, you really need to be able to very accurately characterize both your concentration and your viscosity, because the increases in a small range can be pretty significant. And that's the need of accurate and reliable measurements. Here it's a little bit more extensive over a small range of temperatures for the same formulations or excerpt of those formulations of BSA in PBS and BSA in water, but for a few temperatures. As you can see, you can characterize pretty well the behavior of all those. You can see how the difference between the two buffer solutions are most significant at higher concentrations, as you will expect. And you can see how they all follow very similar behavior depending on temperature, at least within this range. One thing that I want to mention is that all these measurements that I show are based on measurements performed with 100 microliters of each of the solution, performing several shear rates, several repeats, and in summary, a large number of measurements out of a single loading syringe. For some of you, that might not be sufficient. If that's the case, VROC Initium features a sample retrieval feature. So what that means is that you can load your sample, pump it through your system, and do your measurements of viscosity, different temperatures, different shear rates, whatever it is that you're interested on. And then once you're done with that syringe, you have pumped the 100 microliters that you loaded, you can actually go back and retrieve that sample into the syringe. Once you do that, you have two options. One is to actually retrieve the sample with the autosampler and load it back into the vial, which is very interesting if you want to recover that sample to do some other testing and you're really very limited in volume. The other option is to continue your testing inside the unit and actually use the sample in the syringe to retest again and get more repeats the shear rates, get more shear rates if you want more resolution in your viscosity curve, get more temperatures, again if you want more resolution in your viscosity versus temperature curve, and so on. So this sample retriever feature will allow you to study things such as shear stability, thermal stability of your sample, and as I mentioned, recover your sample and use it for some other kind of measurement or study. Here we have a summary of measurement times and cleaning times. For those of you who are familiar with VROC technology, a single point measurement of viscosity typically takes less than a minute. In fact, in most cases, it's just a few seconds that you're pumping your fluid and you're getting your value of viscosity. In the case of VROC Initium, cleaning and drying using our standard protocols, and that might depend a little bit on what sample are you using, what the solvents require for your sample, and so on. But cleaning and drying, it's between 10 and 15 minutes. So you can test about 4 samples an hour. What that turns into is that you can test a full 40 vial rack in about 10 to 12 hours. And you can test something like a 96 volt plate in a day. Which for some of you might think that is quite a bit, but you have to think that once you set up this measurement, the whole job is going to be performed unattended. So you're basically just letting the instrument do all the work for you, including loading of the samples, the measurement, and the cleaning of the instrument in between samples. So here is a summary of the automation capabilities. All of it is performed using an XYZ autosampler that you can see in this GIF doing its work. So you're going to be loading samples into the instrument, then the autosampler is going to go to the cleaning port and then clean itself, and so on. So this is going to offer you your high throughput automatic viscometry or rheometry measurements. As I mentioned, it's compatible with 40 vial racks and 96 volt plate, but it can be extended to other different types of plates. This is fully configurable. The autosampler is mounted with a 100 microliter syringe with a 19 gauge needle that allows you to load pretty high viscosity samples up to 1000 millipascal seconds or centipoise. So that's basically how it works. All right. So now I wanna discuss a little bit how I guess sort of like the workflow for doing the testing with VROC Initium works, and a little bit the features of the different features of the software. So first, in that flow, you will have your sample preparation. So you will prepare your different sample, load it into vials or into your 96 volt plate or into whatever plate that you want to use. And then you will have to determine your job or recipes to do just those measurements. For those, you will have to determine things like the sample loading protocols that you want to use. You might want to do a quick check of viscosity of a specific sample, and you might want to just load it manually. Or you might want to do the auto loading of the samples, and then you will have to set up some parameters such as how fast do I want the sample to be loaded, how do I want my autosampler syringe to be clean, what solvents do I want to use, things like that. Once you have that, you want to go into the next step, which is the measurement protocol. And for that, you have really a lot of flexibility of the things that you can do. You can do a single point measurement. You can do that single point at the fixed shear rate that you are interested on. You can do that single point as an automatic measurement where the instrument is going to determine what's the appropriate shear rate for that specific sample. You can also have a shear rate sweep where you determine I want 5 shear rates between 100 and 1000. That's what I want. So that's what you set and measure. Or similarly, you can have a temperature sweep. And then after that, you have to determine what's your cleaning protocol. So we provide with quite a few factory settings for different protocols based on water-based protein solutions, but there is also a lot of flexibility depending on the solvents that you want to use and how you want to clean your syringes and the instrument itself. So of course, the user can define its own cleaning protocol. So this is how basically VROC Initium software looks. This is the advanced test tab within the experiment tab. So here you have quite a few features. You can select your different vial racks. Here you have an example of a 96 volt plate. You have a number of recipes that you can apply for testing that unit, and that if you choose a recipe, it will automatically load whatever sample loading protocol, measurement protocol, and cleaning protocol is associated to the recipe. So if that's the case, you can just do that single test to a single vial or to a number of vials here, and that will perform automatically the loading, the measurement, and the cleaning. And those steps you can also perform separately if for some reason you're interested in stopping in between each of those. The other tab that you can see in the experiment design is the job tab, and that's a lot of more useful if you're setting up this very extensive studies with a whole rack. So in this case, we don't have set up the 96, we have 40 vial rack, and we have tested a number of samples, each of them is in a different vial, and we're doing different measurements from, I think most of these are the BSA solutions that I show the data in the previous slides, and you have measurements at different temperatures, different shear rates, and so on. So this is how your job will look with the different recipes that have their own auto-sampler loading protocols, measurement protocols, and cleaning protocols. So in order to populate that previous table with the different recipes or protocols, you need to generate those. And we provide a large number of factory settings, but you can create your own. Basically, the first thing that you will have to occur is the loading. You have two options, manual or automatic loading. And basically, you set some of the parameters of the loading itself, such as loading speed or how much you want to inject your needle into the vial that you're loading from and things like that. And you also need to set the auto-sampler cleaning protocol. So you will flash the different solvents for some given amount of time through your auto-sampler syringe and then dry it for the next sample, for example. The next will be to set up your measurement protocol. Here you have also quite a bit of flexibility in terms of the shear rates that you want to measure, or the temperature that you want to measure at, and also you can configure here what's your criteria for stability in the temperature in terms of how long you want the temperature to be kept within a window of plus minus some uncertainty that you want on your temperature control. Once you have set up your measurement protocol, you can save it, move on and go into your cleaning protocol. Again, what you're going to have to determine here, it's the different paths that you want to clean and the solvents that you want to use. You will use different times to pump those solvents and then finally pump air through the system and dry it and give it ready for your measurements. Once you have your loading, measurement, and cleaning protocol set up, you can actually link all those together into different recipes. And once you have a recipe that includes loading, measurement, and cleaning protocol, you can very easily and very quickly apply it to a specific sample that you want to measure. So that makes the setting of the different jobs very quickly and very convenient. So once you're done with this, you run your job. You basically can just go home and let the instrument do its work. And when you come back, you will go into the data. And this is basically how a run will look. You will have your run. You will have the segment that we're looking at right now. This is a pretty high concentration solution, actually. You can see viscosity is about 80 centipoise. And we have looked at the viscosity as a function of shear rate. And you can also see the shear stress as a function of shear rate in this plot. For those of you that are familiar with VROC, this is very similar to the kind of data that you can look on the screen on that instrument as well. It's pretty useful to get a good, quick idea of what's going on with your sample. From here, once you have selected the different runs or jobs that you are interested on, you can actually export in several formats. You can export Excel, you can export CSV, and you can export in PDF. And I have a couple of examples of how these reports actually look. This is an example of the Excel report. So basically you have a summary with all your different segments, the viscosity that was measured during that segment, and then some other parameters such as, you know, shear stress, shear rate, and things like that. The temperature of your chip, your tray, your syringe, and sample name. You have some additional information about the unit, the user, the chip that you're using, and things like that. The other alternative for exporting data, it's a PDF report, and this is basically how it looks. It goes from run to run. It plots all your segments as a function of viscosity versus time during the measurement. It also shows the viscosity versus shear rate. In this case, all the segments were measured at the same shear rate. And it shows you the temperature and the pressure versus position for inside the cell, VROC cell. So this can help you create a quick report that you can use to look at the viscosity of your sample without doing much analysis. All right, so summing up the measurement capabilities of VROC Initium, as we mentioned, is the ultimate high-throughput screening tool for viscosity measurement of formulations, different formulations. You can do studies of injectability of protein therapeutics, whether those are Newtonian or non-Newtonian, because the instrument allows you to get to pretty high shear rates. You can study do stability studies of your protein therapeutics. You have quite a bit of flexibility in terms of the temperatures that you want to study, or the different formulations with different denaturants and so on, or different excipients. You can study the kinetics of chemical reactions or degradation or denaturation, as you can do measurements as a function of a given time. So you can see how your system is changing with time at a given temperature, different temperatures, at some kind of reaction taking place, and so on. You can do solubility studies, and you can study molecular side or hydrodynamic radius in terms using intrinsic viscosity measurements. So this is a summary of the main applications that we are targeting with the instrument. Some of the additional features of the instrument that we have probably not covered in the webinar is that it has an optional 21 CFR Part 11 compliant. It uses a database to store all the data and protocols with user access control, which can be accessed from a different computer to do data analysis and so on. In future release, we will include some data analysis tools that I didn't cover today. Those will include features such as overlay of data, comparison of data sets or jobs, curve fitting to different models for the viscosity versus shear rate, or the viscosity versus temperature, and so on, pass non-pass criteria, model fitting, and so on. So with that, I would like to thank you all for attending this webinar. I would like to remind you about our workshop next week in New Jersey. If you're interested, you're still in time to sign in for the workshop. If you cannot make it to New Jersey next week, you can always send us an email and let us know that you are interested on a workshop or a demo of the instrument, because we will be doing some more workshops and some demonstrations of the instrument later this year. And with that, I want to thank you all again, and we will be taking some questions in a couple of minutes.